Welcome! In this session, we will explore an interesting problem called continuous subarray sum. Together, we'll break down the problem, analyze potential approaches, and work toward an efficient solution. Let's dive in and get started. In this problem, you are given an integer array called nums and another integer k. The goal is to determine whether there exists a continuous subarray within nums, meaning a sequence of adjacent elements that has a sum which is a multiple of k. Importantly, this subarray must have at least two elements. If such a subarray exists, the function should return true, otherwise, it should return false. Now, a subarray is just a contiguous segment of the array, and it must not be empty. For inputs, nums can have anywhere from 1 to 100,000 elements, and each element can range from -1 billion to +1 billion. The integer k can also range from -1 billion to +1 billion, but it will never be 0. The output is a Boolean value, either true or false, depending on whether a valid subarray exists. Let's look at some examples to clarify how this works. In the first example, we have the array nums equal to 23, 2, 4, 6, 7, and k equal to 6. The output in this case is true. Why? Because there is a subarray, 2, 4, within the array that has a sum of 6, which is a multiple of 6. Remember, a subarray must have at least two elements, so this satisfies the size requirement as well. Since we found at least one valid subarray, the function returns true. Let's consider another example to explore a different outcome. In the second example, we are given nums as 23, 2, 6, 4, 7, and k is 13. This time, the output is false. Here, no subarray of size at least 2 exists where the sum of the elements is a multiple of 13. While there are contiguous subarrays within the array, their sums do not meet the required condition. For example, the sum of 2, 6 is 8, which is not a multiple of 13, and the same applies for other subarrays. Since no valid subarray is found, the function correctly returns false. Now, let's examine one more example to see another valid case. In the third example, nums is 5, 0, 0, 0, and k is 3. The output here is true, and the reasoning is as follows: the subarray 0, 0 has a sum of 0. 0 is considered a multiple of any non-zero integer, including 3, so this subarray satisfies the condition. It also has the required size of at least 2 elements. Therefore, the function returns true. Now, let's consider the constraints and edge cases. The array length can be as small as 1 and as large as 100,000, so our solution must handle both small and very large inputs efficiently. Values in the array can also be very large, either positive or negative, so we need to account for potential edge cases like arrays full of zeros, or when no subarray sums to a multiple of k. Additionally, since k can be negative, our solution must handle that correctly as well. To solve the problem of finding if there exists a subarray with a sum that's a multiple of k, we first consider the brute force approach. The intuition here is straightforward: iterate through all possible subarrays of size at least 2, calculate their sums, and check if the sum is divisible by k. For implementation, this means using 2 nested loops, one to select the starting index and another to iterate over the potential ending indices, computing the sum for each subarray and checking the condition sum %k equals 0. While this method is simple, it is computationally expensive, with a time complexity of n squared, due to the nested loops. Additionally, it has a space complexity of 1, since we are not using any extra storage. However, the downside is clear: this approach becomes impractical for large arrays, especially when dealing with thousands of elements. To address this, we shift to an optimized approach using a hash map and modulo arithmetic. The key insight here is that if the sum of a subarray is a multiple of k, then the cumulative sum modulo k at the start of the subarray must equal the cumulative sum modulo k at the end of the subarray. By tracking these remainders in a hash map, we can efficiently identify whether such a subarray exists without explicitly computing all subarray sums. Furthermore, to ensure subarray length is at least 2, we store the index of the first occurrence of each remainder and check the distance between indices. This approach leverages cumulative sums and remainders to streamline the solution. To implement the optimized approach, we start by initializing a hash map to store remainders and their earliest occurrence index. As we iterate through the array, we calculate the cumulative sum and determine the current remainder modulo k. For each remainder, we check if it already exists in the hash map. If it does, we verify whether the distance between the current index and the stored index is at least 2. If so, this indicates the presence of a valid subarray, and we can return true. If the remainder is not in the hash map, we store it along with the current index. Additionally, we handle the special case where k is 0, which requires checking for consecutive zeros in the array. This approach improves efficiency significantly, as it operates with a time complexity of O(n), stemming from the single traversal of the array, and a space complexity of O(n), due to the hash map. By storing only remainders and their indices, the memory usage remains manageable, even for large inputs. When evaluating the trade-offs between the two approaches, the brute force method stands out for its simplicity and ease of implementation. However, its computational expense makes it unsuitable for large arrays, as it quickly becomes inefficient. On the other hand, the optimized approach using a hash map is slightly more complex to implement, but it is far more efficient, reducing the time complexity to O(n). This makes it a much better choice for competitive programming in real-world scenarios where performance matters. In conclusion, the hash map-based approach strikes a balance between efficiency and scalability. By leveraging modulo arithmetic and cumulative sums, it provides a robust solution that is both elegant and practical, making it the ideal strategy for solving this problem. To solve the problem, we are tasked with determining if there exists a continuous subarray of at least size 2 in the given array num such that the sum of the subarray is a multiple of k. The brute force approach starts by validating the input to ensure that the array is not empty and that k is non-zero to avoid errors during division. Then, we iterate through all possible starting indices of subarrays using an outer loop. For each starting index, an inner loop generates all possible subarrays of size at least 2 by iterating through the ending indices. For each subarray, we calculate the sum and check whether it is divisible by k. If any subarray satisfies this condition, we return true. Otherwise, after all iterations, we return false. While this approach is straightforward, it is computationally expensive, with a time complexity of O(n squared). To address this inefficiency, we look at optimization techniques that leverage cumulative sums and modular arithmetic to achieve a faster solution. The optimized solution uses the concept of prefix sums combined with modular arithmetic. The key idea is that if two prefix sums have the same remainder when divided by k, then the sum of the elements between those two indices is divisible by k. We maintain a running cumulative sum of the array and calculate its remainder modulo k at each step. To track remainders efficiently, we use a hash map that stores the first occurrence of each remainder. As we iterate through the array, we check whether the current remainder has been seen before. If it has, we ensure that the distance between the current index and the stored index is at least 2 to form a valid subarray. If the remainder has not been seen, we store the current index in the hash map. Additionally, we handle edge cases such as negative remainders by normalizing them to positive values. This approach significantly reduces the time complexity to O(n), while using additional space for the hash map. The optimized solution provides several key insights. First, the brute force approach, while simple, has a time complexity of O(n squared, which becomes impractical for large arrays. In contrast, the optimized approach reduces the time complexity to O(n) by leveraging prefix sums and modular arithmetic. The use of the modulo operation allows us to efficiently track the cyclic properties of the cumulative sums, identifying subarrays whose sums are divisible by k without explicitly calculating the sum for every subarray. There is, however, a trade-off between time and space complexity. The optimized approach requires O(n) additional space for the hash map, which stores the first occurrence of each remainder. The data structures used are straightforward but essential: a hash map for constant time lookups of remainders and a running prefix sum to compute subarray sums efficiently. The pseudocode outlines the algorithm step by step, including how we handle edge cases such as negative remainders and initializing the hash map with a remainder of 0 mapped to index -1 to handle scenarios where the subarray starts at the beginning of the array. The pseudocode continues by showing the final steps of the implementation. If a remainder is not already present in the hash map, we store the current index of the remainder. Finally, if no valid subarray is found by the end of the iteration, we return false. The time complexity of this approach is O(n), as we only pass through the array once, performing constant time operations for each element. The space complexity is O(min)(n) k, because the hash map stores at most k unique remainders, as remainders are bounded between 0 and k1. We also account for edge cases to ensure robustness. For instance, if the array consists entirely of zeros, any subarray of size at least 2 is valid since the sum will always be 0, which is a multiple of any k. Special handling is required for k equals 0 to avoid division by 0, and for negative values of k, we normalize the remainders to ensure consistency. Short arrays with fewer than 2 elements are immediately ruled out by returning false. To visualize the algorithm, consider the example where nums equals 23, 2, 4, 6, 7, and k equals 6. We calculate the prefix sums as 23, 25, 29, 35, 42, and the remainders modulo 6 as 5, 1, 5, 5, 0. Using the hash map, we track the first occurrence of each remainder. At index 0, we add remainder 5 to the map. At index 2, we encounter remainder 5 again, and the distance between the current index and the stored index is 2, indicating a valid subarray. In another example, with nums equals 1, 2, 3, and k equals 5, the prefix sums are 1, 3, 6, and the remainders are 1, 3, 1. Here, remainder 1 is first seen at index 0 and again at index 2. The distance of 2 confirms a valid subarray. These examples demonstrate how the hash map efficiently identifies valid subarrays using the cyclic properties of modular arithmetic, making this approach both elegant and effective. This implementation solves the problem of checking if there exists a continuous subarray of at least size 2 whose sum is a multiple of k. The algorithm uses the concept of prefix sums and modular arithmetic to achieve an efficient solution. Explanation. 1. Initialization. Start by creating a dictionary remainder underscore map to store remainders of prefix sums modulo k and their first occurrence indices. This helps track repeated remainders efficiently. Initialize it with 0, -1, to handle cases where a subarray starting at index 0 satisfies the condition. 2. Iterate over the array. Use a loop to iterate through the nums array, maintaining a running sum current underscore sum of elements seen so far. 3. Compute the remainder. For each new element, compute the remainder of current underscore sum when divided by k. This operation reduces the problem to finding repeated remainders, which signify subarrays whose sums are multiples of k. To avoid issues with negative remainders, Python's % operator ensures the remainder is positive. Check for repeated remainders. If the current remainder has been seen before, check the distance between its previous occurrence and the current index. If the distance is greater than 1, a valid subarray exists. Return true immediately. 5. Store new remainders. If the remainder hasn't been seen before, store it in remainder underscore map with the current index as its value. 6. Return false if no subarray found. If the loop completes without finding any valid subarray, return false. Time and space complexity. Time complexity. The algorithm runs in O(n), because we traverse the array once, and dictionary operations, insert and lookup, are O(1) on average. Space complexity. The space used is O(min)(n) k for the dictionary, as there are at most k unique remainders. This approach is efficient and avoids the pitfalls of a brute force solution, which would require nested loops and have a time complexity of O(n squared). The use of prefix sums and modular arithmetic ensures correctness and optimality. Here, we start by importing the necessary packages and defining our solution class. The method checkSubarraySum takes an array of integers nums and an integer k as input. The goal is to determine if there exists a continuous subarray of at least 2 elements whose sum is a multiple of k. To achieve this, we use a hash map called remainderMap to store the remainders when the cumulative sum is divided by k, along with the index of their first occurrence. We initialize the map with a key value pair of 0 and -1, which helps handle edge cases, such as when the subarray starts at the beginning of the array. Next, we declare a variable current sum to keep track of the cumulative sum as we iterate through the array. Inside the loop, for each element in nums, we add it to current sum and calculate the remainder when divided by k. If k is not 0, we use the modulo operator to compute the remainder, otherwise, we simply assign the cumulative sum as the remainder. This ensures that we handle cases where k is 0 gracefully. Now, if the remainder has been seen before in the map, it means there's a subarray between the previous occurrence of this remainder and the current index whose sum is a multiple of k. We then check if the length of this subarray is greater than 1 by comparing the difference between the current index and the stored index. If the condition is met, we return true. Otherwise, if the remainder is not already in the map, we add it along with the current index to track its first occurrence. Finally, if the loop completes without finding any valid subarray, we return false. This ensures that we only return true when we have positively identified a subarray of at least two elements whose sum is divisible by k. The algorithm efficiently handles edge cases, such as when k is 0 or when the subarray starts at the beginning of the array, thanks to the initialization of the remainder map and careful handling of remainders. By leveraging the properties of remainders and the hash map for quick lookups, this implementation achieves optimal performance while maintaining clarity and correctness. To solve this problem, we use a dictionary called remainder_map to keep track of remainders when the cumulative sum of the subarray elements is divided by k. Initially, this dictionary contains the key value pair 0-1, which represents the remainder 0 at a fictitious index -1. This helps handle cases where the subarray starts from index 0. We also initialize current_sum to 0. Now, as we iterate through the array, we update current_sum by adding the current element. For the first element, 23, the cumulative sum becomes 23. Computing the remainder when 23 is divided by 6 gives 5. Since 5 is not already in remainder_map, we store it along with the index 0. Moving to the next element, 2, the cumulative sum updates to 25. The remainder of 25 divided by 6 is 1. Again, since 1 is not in remainder_map, we store it with the index 1. At this point, our dictionary has the mappings 0, -1, 5 o'clock, 1, 1. Next, we consider the third element, 4. Adding 4 to the cumulative sum gives 29. The remainder of 29 modulo 6 is 5. Now, we find that 5 already exists in remainder_map at index 0. This indicates that the subarray from index 1 to 2 has a cumulative sum that is divisible by 6 because the difference in remainders is 0. We calculate the length of this subarray as remainder_map, 5, which is 2, 0 equals 2. Since this length is greater than 1, we can conclude that such a subarray exists, so we return true. In the next example, we are given the array 23, 2, 6, 4, 7, and k equals 13. We start with the same initial setup, remainder_map equals 0, -1, and current_sum equals 0. For the first element, 23, the cumulative sum becomes 23, and the remainder when divided by 13 is 10. Since 10 is not in remainder_map, we store it along with the index 0. For the second element, 2, adding it to the cumulative sum results in 25. The remainder of 25 modulo 13 is 12. Since 12 is not in remainder_map, we store it with the index 1. Next, for the third element, 6, the cumulative sum becomes 31. The remainder of 31 divided by 13 is 5, which is also stored in the dictionary with the index 2. For the fourth element, 4, the cumulative sum updates to 35, and the remainder of 35 modulo 13 is 9. This is a new remainder, so we add it to remainder_map with the index 3. Finally, for the fifth element, 7, the cumulative sum becomes 42, and the remainder when divided by 13 is 3. This remainder is also new, so we store it with the index 4. At this point, we have processed the entire array, and no remainder repeats in a way that satisfies the condition for a subarray length greater than 1. Therefore, the output for this example is false. In the third example, we are given the array 5, 0, 0, and k equals 3. The initial setup remains the same as before, with remainder_map equals 0, -1, and current_sum equals 0. For the first element, 5, adding it to the cumulative sum results in 5. The remainder of 5 modulo 3 is 2. Since 2 is not in remainder_map, we store it with the index 0. For the second element, 0, the cumulative sum remains 5 because adding 0 does not change the value. The remainder of 5 divided by 3 is still 2. This time, we see that 2 is already in remainder_map at index 0. However, the length of the subarray, calculated as remainder_map, 2, is 1 and 0 equals 1, which is not greater than 1. Therefore, we continue processing the array. For the third element, 0, the cumulative sum remains 5, and the remainder when divided by 3 is still 2. Once again, we find that 2 is in remainder_map, this time at index 0. Now, the subarray length is remainder_map, 2, which is 2, 0 equals 2. Since this length is greater than 1, we confirm that a valid subarray exists. Therefore, we return true as the final output for this example. This concludes our solution walkthrough, demonstrating how the remainder-based approach efficiently checks for subarrays with sums divisible by k. The time complexity of this algorithm is O(n), where n represents the length of the input array nums. Let's break this down step by step. First, the algorithm uses a single for loop to iterate through the entire array, and since the loop runs exactly n times, this contributes O(n) to the overall time complexity. During each iteration, the cumulative sum is updated using the operation current_sum plus equals nums, I. This is a constant time operation, or O(1), because it simply adds the current element to the sum. Additionally, the algorithm performs a modulo operation, current_sum%k, when k is not 0. This step also takes constant time, or O(1), as it just calculates the remainder. These steps together ensure that the bulk of the work done is linear in relation to the size of the input array, making the overall time complexity O(n). Next, let's consider the hash map operations. During each iteration, the algorithm performs a constant time lookup to check if the current remainder exists in the hash map, using remainder in remainder_map. In the worst case, it also performs a constant time insertion, such as remainder_map, remainder equals I. Hash maps are highly efficient, with average time complexities for insertion and lookup being O(1). When we combine all these steps, we get O(n) for the iteration, O(1) for updating the cumulative sum, O(1) for the modulo operation, and O(1) for hash map operations in each iteration. Summing these contributions, we arrive at an overall time complexity of O(n). Shifting focus to space complexity, the algorithm's space usage is determined by the size of the hash map. The hash map stores the remainders of cumulative sums modulo k as keys, and their first occurrence indices as values. Since the number of unique remainders is limited by the divisor k, the hash map will store at most min, n, k entries. In the worst case, where all remainders are unique, the space complexity becomes O, min, n, k. The space complexity also includes the additional scalar variables used in the algorithm, such as current_sum, remainder, and others. These require constant space, which is O(1). However, the total space complexity is dominated by the hash map, so the overall space complexity remains O, min, n, k. To put this into perspective, let's compare our algorithm to a brute force approach. The naive solution involves checking all possible subarrays of nums to see if their sum is divisible by k. Generating all subarrays takes O(n squared, since there are roughly n subarrays of average length n/2. Calculating the sum for each subarray adds another O(n) in the worst case. This results in a staggering total time complexity of O(n cubed). The brute force method doesn't use any additional data structures, so its space complexity is O(1). While simple, this approach is computationally expensive and impractical for large inputs. In contrast, the optimized solution drastically reduces the time complexity to O(n) by avoiding redundant calculations. It achieves this through the use of cumulative sums and remainders, which allow us to check divisibility conditions efficiently. While the space complexity is higher at O, min, n, k, due to the hash map, this trade-off is well worth it given the performance improvement. Now, let's analyze the best, average, and worst-case scenarios of the optimized algorithm. In the best-case scenario, the solution might be discovered early, such as when the first subarray meets the divisibility condition. While the algorithm can terminate early in such cases, its big O time complexity is still O(n), because we analyze the entire loop in terms of its linear growth. In the average case, the algorithm typically scans through the array, building the hash map as it goes. most remainders will not repeat until later in the array, but the overall time complexity here remains O(n), due to the linear nature of the process. Finally, in the worst-case scenario, no valid subarray is found. This means the algorithm processes all n elements in the array, resulting in O(n) time complexity. The hash map will also store up to O(min)(n) keys in this scenario, which defines the space complexity. To mathematically prove the big O analysis, consider that each operation inside the loop, including updating the cumulative sum, performing the modulo operation, and hash map lookups or insertions, takes constant time, or O(1). Since the loop runs n times, the total time complexity becomes O(n) multiplied by O(1), which simplifies to O(n). For space, the hash map stores at most min(n) k unique keys, leading to O(min)(n) k space complexity. This analysis confirms that the optimized solution is significantly more efficient than the brute force approach, particularly for large input sizes, making it a robust choice for this problem. When solving this problem, there are a few common mistakes that can trip you up. First, handling negative numbers incorrectly during modulo operations is a frequent issue. Some programming languages will return a negative result for expressions like -1%5, which might not align with your expectations. To address this, always ensure your modulo results are non-negative by adjusting the calculation if needed. Next, it's easy to overlook edge cases. For instance, subarrays with only 2 elements, arrays of the minimum allowed size, or scenarios where k equals 0 can all behave differently. Verifying the constraints and testing these edge cases is crucial. Another common pitfall is relying on an inefficient brute force approach. Checking all possible subarrays with O(n)³ or O(n)² complexity might seem straightforward, but it will fail for larger inputs due to time limits. Instead, optimizing with techniques like prefix sums or hash maps is key. Finally, using the wrong data structure can lead to inefficiencies. For example, a list instead of a hash map for prefix sums can make lookups much slower. Understanding the trade-offs between data structures ensures your solution is both correct and efficient. Another challenge arises when candidates misinterpret the problem requirements. In questions like subarray sum divisible by k, it's easy to confuse subarrays with subsequences or to forget that subarrays can start at index 0. Always ensure you fully understand and clarify the requirements. Now, during interviews, there are strategies that can help you shine. Start by explaining your thought process clearly. Even if your initial approach is brute force, discussing its limitations and then refining it to an optimized solution demonstrates critical thinking. When optimizing, focus on patterns such as prefix sums, sliding windows, or properties of modulo arithmetic. For example, the condition prefix_sum j, prefix_sum I, %k = 0 can be simplified to prefix_sum j, %k = prefix_sum I, %k. Using small examples to validate your approach ensures you're on the right track, and proactively addressing edge cases shows thoroughness. These steps not only help you solve the problem but also leave a positive impression on your interviewer. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 560 focuses on subarrays that sum to a target value, while LeetCode 974 and 523 deal with subarray sums divisible by a given number. LeetCode 325 is another variation, where the goal is to find the maximum size of a subarray with a specific sum. These problems build on similar concepts and strengthen your problem-solving skills. When it comes to approaches, the brute force method involves checking all subarrays and calculating their sums individually. While this is simple to implement, it's inefficient with a complexity of O(n)³, making it impractical for large inputs. A more efficient alternative is to use the prefix sum technique combined with a hash map. Here, you store prefix sums as you iterate through the array and check for sums that satisfy the condition. This approach has a complexity of O(n), balancing speed with a trade-off of additional space for the hash map. Finally, the sliding window technique provides another effective approach for some subarray problems. This method dynamically adjusts the window size as you traverse the array, maintaining efficiency with a single traversal at O(n) complexity. However, it's important to note that sliding windows require careful handling of indices to ensure correctness. Additionally, they may not be suitable for all problems, particularly those involving modulo operations. Understanding when and how to apply these techniques is vital for crafting optimal solutions. By mastering these methods and variations, you'll be well prepared to tackle a wide range of subarray problems. Great job! To recap, we tackled the continuous subarray sum problem, explored its nuances, and implemented an efficient solution. Remember, mastering hash maps and modular arithmetic can significantly enhance your problem-solving skills. Thank you for joining, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!